Welcome to Notes 15.4. We're going to have 2 days of vectors, so this is our first day looking at vectors. If you've had a little experience in physics, you'll see that this has a direct application to several things in physics. So today we're just going to look at vectors themselves and get a good understanding of those, and then our next lesson, 15.5, we'll go ahead and look at vectors as they apply in calculus. So first of all, what in the world is a vector? Let's clear up one thing. Scalar quantities are described by a single number located on a horizontal or vertical number line. Best example is temperature. Temperature is a scalar quantity. Think of temperature as a single number that moves up and down along a vertical scale. But we have some quantities that need more than one dimension to describe them, and that's where vectors come in to speak. The best example is wind. When weather people are reporting, you've seen some of their weather maps, and they talk about the wind. The wind needs two things. It needs to be described in its magnitude or strength or amount, and which direction it's blowing. Let's take a look at an airplane and see how wind affects that, and see how vectors apply to that. So if you can imagine a plane flying, obviously the propeller is sending it in one direction. There's a force that is provided by that propeller that's moving the plane in the direction of the propeller. But if there is a wind acting upon it, say a wind that's coming, in this case, in the front and going from left to right, that's going to affect where the plane goes. The plane is actually going to be traveling in a direction that would take it something like this. And vectors help describe that motion. You can see we've got a vector, force vector that has the plane going in this direction, another force vector shown by the wind, and the resulting vector, which I've highlighted in yellow, will be the actual path that plane is taking, because that vector there is the direction of the resultant force upon that plane. So you can see from this quick description that vectors are used to represent two quantities, or sometimes even more. A two-dimensional vector is represented by order pair xy. Those are called the components of the vector. So we've got an x component and a y component. A vector is a directed line segment. The length of the line segment represents the magnitude or strength of that. And then the direction the vector points is obviously the direction that speed or force, whatever the case is traveling. The two let me describe to you what we mean by a same vector. The definition of that would be two arrows with the same magnitude and same direction would be the same vector, regardless of where the arrows are placed in the plane. Let's take a look at a couple examples here. Let's call this vector A, this vector B, this vector C, and this vector D. You'll see I've used this vector symbol above it. You may say it's just the same as array, but we try and leave the bottom half of the arrow off so it doesn't look like our geometry arrays that we have. But if you do draw them, it's not that big of a deal. So you can see that symbol is shown here. Many times you'll see online and in textbooks the vector is going to be in a bold print. So we've got four different vectors here, and we're going to compare them to vector B. First of all, I want to note to you that B and C are equal vectors to each other. Why? Because they are both acting in the same direction. If I measure the angle there, they would be the same, and if I measure the length of them, they would be the same. Now, if we look at D, D has the same length as B, but since it's not in the same direction, oops, that's supposed to be a D, B and D are not equal to each other. If I compare the lengths of A and B, I do find out that they're the exact same lengths, but obviously B is going in this direction, A is going in that direction, they're going in opposite directions. So what we could say is that vector B is equal to the opposite of vector A. So if I just change the direction of A to go in the opposite direction, then I'll have a vector that is equivalent or equal to vector B. We also have a zero vector that has zero length to it, and that's just a plain old point. No need to define its direction or length because it simply has zero length. As I showed up here in our previous example, if we have an opposite vector, just put a negative sign in front of it, and you're going to have the same magnitude, but the vector is going to go in the opposite direction. So up above, if I wanted to say what is the opposite vector of D, I would measure that same length, and I would move that vector and put it so that it is initial point and ending point are opposite, and this would be the opposite of D. As I tried to show before, and just to summarize here, equal vectors have equal magnitude in the same direction. If we want to represent or say the length of those vectors or the magnitude or strength of those vectors, we use what appears to be an absolute value symbol of them. Another more popular one is just to double up on that, but either one of those are interchangeable, and you'll find them used in various textbooks depending on what the author chooses. Number 10 point that I want to make out is this idea of a standard position. If we take our vector and put its initial point at the origin, 0, 0, and its terminal point wherever it's leading, then that vector is called in standard position. So I could say A, or excuse me, let's look at vector C up here. If I define this as the origin, then C is in standard position. I would have to take B and move it over here to put it in standard position. Next, want to talk about component form. Component form is written just like you would write any ordered pair if you're talking about a point on a coordinate grid. But component form, we just use the X and Y symbols like a point. I prefer, and most authors would prefer, that you use these symbols for your parentheses just to help designate that it's not point XY that you're talking about, but you're talking about vector XY. And then what I want to do is just make sure you understand what we're talking about in this one. In component form, think of a right triangle where x represents the horizontal displacement of the vector. So if I have vector v here, the initial point here, its terminal point down here, I can think of the x component would be this horizontal displacement that I would go in this direction. And then as I go from here, kind of like a rise over run setup, my y component would be the direction that I'm going vertically. So in this case, we could say that, let's say x equals 5 and y equals, say, -7. So vector v would be defined as the ordered pair 5, -7. Also want to talk about the length or magnitude of a vector. You can see that it's a simple application of Pythagorean theorem. If we have a x component and a y component. We just do Pythagorean theorem to get the actual length or magnitude of that. Its direction will be using our trig. So in this example here, you can see I have a horizontal component, which would be my x, and then a vertical component, which would be y, and the direction that I want to travel would be theta. And theta is measured the way we've been commonly measuring all of our measurements, with the horizontal or x-axis as the initial or 0, and then we're going in a counterclockwise direction. So you can quickly see that opposite over adjacent would be the tangent, and that would be the relationship that we would use to describe or even calculate what angle we have or what direction that we're traveling in this one. Next, want to point out some calculations that are going to be required for you to do. Will require you to use this component form. So let's imagine that we have a point here, the initial point of our vector defined by x1, y1, and q as our terminal point, and it has the coordinates x2, y2. So we have a vector, in this case represented by xy, where x is, of course, this distance from here to here, which would be defined as x2 minus x1. That would give us this length here. And then you can see that our rise, this vertical dimension, that is our y component, would be just the difference between the y's, or y2 minus y1. We'll use that to calculate, or excuse me, not calculate, but I guess it is a calculation. You can use this to calculate and report the vectors, components, and component form. Let's do some examples with this one, starting here with a request that we find the component form of the vector, and then sketch the vector in standard position, or with its initial point at the origin. Both of those mean the same thing. So just what we did on our last page, we can look at the initial point here, 2, 1, terminal point, negative 1, 3. So if we take x2 minus x1, we'll get negative 3. Or you can just look at this and say, yeah, I'm going to the left 3. And then y2 minus y1 would give us 2. Or again, you can look at it and say, yes, this vector is going up 2. So this is the component form of this vector v. And then in standard form, all we're going to do is take this initial point and slide it down to the origin and make sure we're keeping the exact same length and direction. So we'd go left 3 and up 2 and draw our new vector in standard position. Let's quickly take a look at this one over here. If you want to, you can figure out your coordinates and then do the subtraction method we did previously, or most likely you're just going to say this vector is going 1, 2, 3, 4, 5, 6 to the right, which would give us an x component of 6, and it's going up 1, 2, 3, which gives us a y component of 3. The vector can be moved with the initial point at the origin, and we'll do the exact same thing. 1, 2, 3, 4, 5, 6, 1, 2, 3. That's our terminal point. We draw that line in there. Next set of examples gives us not the graph, but the initial point P and the terminal point Q. make sure you do check and make sure that you're not switching those around. Follow the directions because vector QP, if Q is our initial point and P is our terminal point, we will not have the exact same answer as what we're going to get here. But you can see it's just a matter of taking the terminal minus the initial. So x2 is -1 minus 2 gives us -4 for our x component. y2 is 9, y1 is 7, 9 minus 7 gives us 2. And we'll do the same thing for the next one. -10 minus a -4 gives us -6. 2 minus a -8 gives us 10. And if you want to check, you'll see that this went up 10 and left 6 to get from this point to that point. And those are the resulting vectors in component form. The next one is asking us to write it in component form, but this time we don't have the initial point and terminal point. What we have is the actual length of the vector and the direction in which it goes. I like to make a little quick sketch of these just to make sure I don't make an error. And so you can see I've gone ahead and put it in standard form, having a length of 5, and then the angle would be 1/6 of pi. So we want to get magnitude and direction of this. So, or excuse me, we're given the magnitude and direction. We need to find our x component and our y component. Just take a look at this. X, of course, is horizontal. Y is our vertical. So trig ratio will apply here. Our cosine will be x over 5. Sine of this direction, angle, will be y over 5. And then you can see that I've gone ahead and just a little bit of algebra to solve cross products or multiply by 5, and then remember my trig, cosine of 1/6 pi is square root of 3 over 2. So my resultant x component of the vector is 5 square roots of 3 divided by 2. I'll do the same thing with the sine function to solve for y, and we get 5/2. And as a result, our component form of this vector v will be 5 square roots of 3 divided by 2 and 5/2. Let's take a look at our next one. The next one gives us a magnitude of 8, and take a look at our direction this time. Our direction starting at 0, clockwise direction, is going 8 pi, or 8 divided by 9, or 8/9 of pi. So we're not quite to 1 pi. We're actually 1/9 of pi away from going 180 degrees or pi radians in direction. So what I've chosen to do is take a look at this triangle here, where I have my x component and my y component, and the angle that I'm going to use for my sine, cosine, will be not the 8/9 of pi, but 1/9 of pi. You'll also see that I slid in a negative sign here because I know x is going to have to be negative because I'm going to the left. Y, of course, is going to be positive. So calculating this, this one ended up being a calculator permitted, gave me this value for my x. And then for my y value, I'll do the same thing. Take my sine function and solve for y, and we get this value. Okay? Which means our resulting vector, vector v, will have an x component of -7.517 and a y component of 2.736. Now, some of you may say, did I need to do that this way? No, you don't have to do it that way. Sometimes this is just the easiest for people to see. But if you wanted to, you could have just done a 8 times the cosine of 8/9 of pi, since that is the direction that we're given. And because we're going 8/9 pi, this is going to result in a negative number. If you remember from your unit circle, that this value of cosine of 8/9 of pi will give you your negative anyway. So however you want to do it, doesn't matter to me. This one is a little bit more visual for those of you who are good at your geometry. If not, you can just substitute in, and the same result will be achieved by using this method. Let's take a look at a couple more examples. Now we're going to have to find the magnitude and the direction of these, and we're not given the initial point and the terminal point. We're just given the actual components of our vector. So magnitude is going to be pretty simple here. I've drawn my picture over here if that helps you. You can see the x component is 4, y component is 5. I've drawn it in standard position, and you'll see that the magnitude is simple Pythagorean theorem. A squared plus b squared, 25 plus 16 gives us 41, so the square root of 41 will be our magnitude. Our direction is simple trig, opposite over adjacent, and then doing our inverse tangent. If calculator is permitted, then we would just put that in our calculator, and the inverse tangent of 5/4 gives us 0.896. Let's take a look at the next one. I do want to point out again my sketch going negative 15 in the x direction, negative 10 in the y direction, which means theta, that angle, is going to be all of this from here to here, starting at 0. Now, what I've chosen to do is similar like I did up in 6, and I just want to look at this triangle here, and I'm going to go ahead and find this angle here, and I've just defined that angle as alpha. And if I have that, then all I'll do is add pi to that, and that'll give me the resulting direction that I'm looking for. Okay, so first of all, before I get to that, took care of the easy part, and that's our magnitude. Pythagorean theorem, 15 squared plus 10 squared, which would be the square root of 325. And then, as I was mentioning before, we'll find this angle by using our inverse tangent, opposite over adjacent, which gives us 0.588 for this angle. And then, to find theta, all I have to do is add pi to that, and the direction angle for this vector will be 3.729. Okay, so, and that should make sense, this being pi. We're just a little bit past that. Next problem is just again, some more practice with your vectors, making sure you understand the rules that are involved in here. If I have two vectors and I add them together, if they're both in component form, it makes the result pretty simple, because all I have to do, as you can see here, is I'm going to take each one of my x components, and if I'm adding, I just add those x components together. And then I'll do the same thing with my y components. I'm just going to add those together, and the sums will be my resultant vector. Sometimes you might have some constant times the vector. Again, easy math. You can see what happens here. All we do is take the x component, multiply it by k, and the y component, and multiply it by the same value. And if you take the opposite of your vector, just take the two components and write them as the opposite values of those. And it probably goes without saying, but we'll make sure you understand here. If we can add vectors by adding their components, we can also subtract vectors by doing the same thing. I'm just going to take the x component, subtract the other x component, and do the same thing with our y components. So let's do some examples that kind of use these. So we're given two vectors, vector A and vector B. First thing, go ahead and calculate the actual magnitude or length or strength of vector A squared plus B squared. A being the horizontal component, -4 being the horizontal component of A, and 3 being the vertical component of A. The result would give us a vector that has a magnitude of 5. To add these two vectors, just like we showed in the rules up above, we're just going to take our -4, add 6, and get 2. Take the 3, add 2, and get 5. The resulting vector will be 2, 5. If we have A minus B, -4 minus 6, -10, 3 minus 2 gives us 1 as our resulting vector. A scalar or a constant multiplication of that would take our -4 times 2 and get -8, our 3 times 2 and get 6. We can even do a combination of these. In this example, you'll see that we're taking our components of A and tripling those, and the components of B and multiplying those by 4. So -4 times 3 is -12, 6 times 4 is 24, and then we'll add those together and get 12. We'll use the same values for the y component. 3 times 3 is 9, 4 times 2 is 8, then add those, and we get a resultant vector of 12/17. Okay? Now, let's do one final thing with our vectors, and that's graph these. So I put all of these out here, most of these already completed, so we'll just do these one at a time. First of all, you'll see that I have some of my vectors as actually just two of the vectors, vector v and u, that I just have in component form. And then I also have vectors A, B, C, and D that are not given to me in component form. They're just given to me in a graph. So what I'm going to do first is, with these, just go ahead and write them in component form. That way I have the numbers available to me. So 3, 6 is A. You can see that B is the 6, 0. And C is to the right 5 and down 4. D is just down 4. So those are the components of those. So now what we're going to do is take these vectors and perform addition, subtraction, even a little bit of multiplication of those. And what I'm going to use is what's called a tip-to-tail method. And what that's describing is how I'm laying out each one of these as I add them together. Okay? The tip is the point, that's the terminal, sometimes called the head. I like to just call it the tip. And the tail is the initial point. And what I'm describing to you is when I lay these out, I'm going to start here. So for example, with the one that I have here, I'm going to start with the one that's highlighted green. And if I'm adding to that, I will add the next one by putting the tail to the tip. Okay? So tip to this tail, and then the resulting vector is shown here in red, going and putting this initial point here and the tip going to the final resting place of the previous one. Let's go ahead and do example A here and make sure we understand what we have here. So first of all, you'll see that I start out by putting vector v. Vector v was left 2 and up 5. So I went left 2 and up 5 on the graph paper. And then since I'm adding u, I'm going to start and I'm going to put tip to tail. And my next one is to the right 6 and down 2. So I'm going to go to the right 6 and down 2. The resulting vector of v plus u will start at my initial starting point and end where the last vector's tip is. So the resulting vector of v plus u will be this vector here. In component form, we could write it as 1, 2, 3, 4, 1, 2, 3. It would be the vector 4, 3. This is, again, the tip-to-tail method for adding vectors using graphing. Okay? Now, I do want to point out a mistake that some people do make when they're doing these. They'll put, for example, they'll write the first vector, let's just say that this is vector A, and then they'll add vector B to it, and they'll put both of them at the same initial point, and then say that this is the resulting vector. That's not how this is done. This would not give me the correct one. For example, in this one here, if I put both of the tails together of v and u went down in this direction, and then tried to get the resulting vector, you can see that I would get something completely different from this. So again, do not put both of them vectors that you're adding together, don't put both tails together. You're going to put the tip to the next one's tail. Another problem that I see many people do is illustrated here. So if I say that this is vector v and I'm adding vector u to it, you can see this time I did it correctly. I started here, I put the tip to the next one's tail, but this is shown incorrectly because this person said the resulting vector went in that direction. Okay, this is wrong. The resulting vector always has to have its tail where the initial vector was started. So again, these are two common mistakes that I see that I want to make sure that you don't do as we go through these. Let's go ahead and take a look at B. In B, the first thing you'll see that I've done is I've drawn vector V to the right, or excuse me, to the left 2 and up 5, and then did it again, left 2 and up another 5. In other words, I've doubled vector V to represent 2 V here. Then we're going to subtract vector A. Vector A is up here. I didn't point out to you, but this is not the same scale as what we're using here, but we're just going to assume that 3 units here will transpose over to 3 units on this one. So you'll see that vector A is going up and to the right, so if we're going to subtract vector A, we're going to have to go down and to the left. So 3, 6 now becomes, for vector A, or the opposite of vector A, it's going to be -3, -6. And that puts us here, which means our resultant vector is not going in this direction like I showed over here. It's going to go starting here at the initial starting point and go in the direction so that the final or terminal point is at the tip of the previous one. And this would be our resulting vector. Let's take a look at C. In C, we're taking vector A and adding vector C to it. Vector A, 1, 2, 3, 1, 2, 3, 4, 5, 6. Vector C is to the right, 1, 2, 3, 4, 5. And down 4, 1, 2, 3, 4, 5. Looks like I was off a little bit. Down 1, 2, 3, 4. So make a quick little change on this one. And C should go in that direction and end up right here, which means our resultant vector of A plus C will be this guy right here. Initial starting point to the final tail. You'll see in D, we're actually going to add 3 vectors. Same exact method we've done before. We just keep putting tip to tail, and we'll do it for 3. We could do it for 4 or 5 or 6. It doesn't really matter. So you'll see I've drawn the first vector, vector D, which was 0, -4. Then, starting here with the tail at the tip of the previous one, B is just to the right 6. Then we'll take C. C was the one that went down and to the right. So we go, I can go down 1, 2, 3, 4. To the right, 1, 2, 3, 4, 5. We end up here. Our resulting vector is going to start from the same starting point that we started with D, and it's going to end up at the final terminal point of C. And our resulting vector will be this right here. That's D plus B plus C. Let's take a look at E. E is going to start out with D, and then we're going to subtract B this time, and then add A to it. So I've shown this one down here. You'll see that D is the down 4. Now subtracting B will no longer go to the right 6, but to the left 6. Then we'll add A. A was to the right 3 and up 6. And our resulting vector will start here at the same starting point and end here. Okay. Let's do our final one. Our final example starts out with A, which is shown right here, the right 3, up 6, and then we're subtracting 2B. This is 1B, and this is another B, all going in the opposite direction of our initial vector B. Then we're going to subtract V. V, as you recall, or see up above, was -5, or excuse me, -2, 5. And so what I've done here needs to be switched around, because you can see that I went ahead and instead of subtracting V, I need to, or excuse me, I added V. That's what's shown here. I needed to subtract V. So instead of going left 2 and up 5, I need to go right 2 and down 5. So let's switch this one out and make that correctly in this direction. And that is subtracting vector V. The result is going to be this guy right here. Okay, So be careful as you go through these, that you're careful to subtract when you're supposed to subtract, and don't mess up on the simple math. And that will be the resulting vector of part F. Yeah? Our final one is just some quick little sketches. Not going to be very, very precise on these. Just going to use a little bit of artistic ability and make sure that I write these in the right direction. So you'll see this one gives us, actually all 4 of these give us the same sketch, and we're just going to modify them to meet this requirement or request. So the first one is just to write the opposite of U. So you can see U started here and went in that direction. The easiest thing for me to do is just put my tail at the same tail and then go in the opposite direction. This could be a U rather than a V. And try and do it about the same length as the previous one. Part B says let's do 2U. 2U is going to start at the same tail, and I'm just going to go in the exact same direction and go twice the length of that. C is similar to what we did up above. It's going to take U and subtract V from it. You'll notice on all of these there is no need to take and slide these down to put them at the origin and put them in standard position. It's probably best that you just leave U exactly where it is, and then I can envision sliding V up here, and since I'm subtracting V, I'll just go in the opposite direction, and again I'm still using my tip to tail method, and my resultant will start at where U was and end up at where the tip of V would have been, or excuse me, the opposite of V would have been. We'll do one more example. This one starts out with U. Here's my starting point. U is there. Again, no need to really move that. I'm just trying to find out what the resultant vector is, but I'm going to add 2V this time. So I can imagine 1V here, 2V there. So my resulting vector will go from here to there, and I have completed a quick little lesson on vectors, vector addition, vector subtraction, and scalar multiplication of the vectors. Hopefully this lesson goes well for you. We'll move on to 15.5 and do our calculus applications in the next video.